Okay, welcome back, students. Let's get into section 1.6. Okay, 1.6 is first order linear differential equations. Okay, not to be confused with, the first order from one of my favorite movies, Star Wars. Okay, so different first order. Okay, first order, meaning that it's first derivative, linear differential equations. Okay, let's define this. A differential equation that can be written in the form a of x dy dx plus b of x y equals r of x, where a of x, b of x, and r of x are all defined on an interval of x is called a first order linear. So we've seen first order before. We've dealt with separable ones before. Now we're dealing with first order linear differential equations. Okay, it's called a first order linear differential equation. Okay, let's taking this guy and dividing him both sides by a of x. Gives, okay, the a of x would be gone in front of that, so dy dx plus, then we get b of x over a of x, but I'm gonna say that b of x over a of x is just another function of x. We're gonna call that p of x. Y, and r of x over a of x, r of x over a of x, again, that's just another function of x, and we're gonna call that q of x. And this is called standard form of our linear differential equation. Okay, the goal here in solving this linear differential equation is that we need to find I of x, which is equal to the e to the power of the integral of p of x dx. Okay, where the constant that I would get from my integration, we're just going to set that equal to 0. Okay, we only need one value, one function that works here. We don't need a family of functions that works, especially since they're just going to get we're going to take the derivative of it later on as well. And we do this so that we get so that we can complete the product rule on the left side of the equation. Okay, so that e to the integral p of x, that's going to help us kind of complete the product rule. Okay, we're going to get a product rule, and then we're going to be able to take the derivative of both sides, and it will work out nicely. Okay. Okay. Here's how it works in theory. If I multiply this e to the integral p of x dx times both sides of the equation dy dx plus p of x y, okay, equals e to the integral of p of x dx times q of x, okay, then what happens is if we kind of distribute this guy, okay, so e integral p of x dx, and then we do dy dx, okay, or we could say that that's y prime. We'll write it like that in a little bit, but dy dx plus e integral p of x dx times p of xy is equal to, okay, q of x, oops, times e to the integral p of x dx. Okay, so how does this help me? Okay, the idea is that if I were to take the derivative with respect to x, okay, of this guy here, e to the integral of p of x dx, okay, times y, okay, if I were to take the derivative of that, that is just the line above. Now, how is that? Well, this comes to us from the product rule, okay? If we were to take the derivative of the second, okay, of the second times the first, derivative of the first, or first times the derivative of the second, we would get this guy here. Okay, this y would become this y prime here. Okay, and derivative of the second times the first. And then what would happen if I took the derivative of the first times the second? Well, the y is just the second. And if I took the derivative of e, well, that's itself, times the chain rule here, okay, times the chain rule, so derivative of e integral, well, the integral of p of x would be big P of x. By the fundamental theorem of calculus, if I took the derivative of an integral, I would just get the original value p of x back out. Okay, so think of it as like we're taking the derivative of this e to the integral p of x dx. Well, that's just, think of that as a, e to the a. Well, that's just e to the a times whatever the derivative of e to the a. Well, if I take a derivative of an integral, I just get the original value out, the original equation out, if I'm going from, say, 0 to x. But we can show that that's going to always be the case, that this e to the integral p of x dx will solve this product rule by taking the derivative of these two pieces. Okay, so I'm basically, that's my factor. My I of X is my factor that's gonna help me complete the product rule. Okay, complete the product rule. We multiply through by that, and it allows me to write the second to last line as the first to last line. This is Q of X. Okay, e to the integral P of X dx. And then what would happen if I integrated both sides here? I would get the integral of this and the integral of this. Okay. And so this would become e to the integral P of X dx, which I think I'm going to call y of x, is equal to, okay, the integral of Q of X, and this would be two functions, okay, of X. This would give me a function, the integral here would give me a function of X times Q of X, and we'd end up having to that, you know, by probably integration by parts. Okay, so more than likely we'd have to integrate that, but it's all based on X. Okay, and then it would be a dx here as well. Okay, so we integrate that, but then what that allows us to do is allows us to solve. I'm gonna call this I of X, my integration factor there. I of X times Y is equal to the integral of Q of X, I of X dx, okay. And then I would divide, okay, dx, and then I would divide by I of X, okay, divide by I of X, keeping in mind that this integration is going to create a constant, and that constant would then be divided by I of X. So just keep that in mind, that we don't just get a constant on the end, we get a constant divided by. So I'm going to put that in. I'm going to say this is Q of X times I of X dx, the integral of that all over I of X, plus some constant of integration, okay, and then over I of X. So we would actually get a polynomial, and actually a rational function of X for this last term here. It would be a rational function of X. And maybe I could combine that with what I got for the integration. Maybe I couldn't, maybe, you know, however I could simplify that. Okay, but that's the basic premise. Okay, so what I don't want you to do is I don't want you to memorize the outcome. Okay, don't memorize the outcome, because there are many different forms of this, but memorize the process. Okay, you don't memorize the outcome per se here. I mean, you could memorize the, like, what is I of X? It's e to the integral P of X. You're going to need to know that, but then, you know, you could try to put this into a formula and crank it out, but it would get messy because you've got integral inside of integral. And so I really want you to memorize the process here. Okay, and let's go through one of these so we can really get to see how does this process work. Okay. Solve dy dx plus 1 over x, y equals e to the x. Okay, so first I need to know, is this a linear, first order linear differential equation? And yes, it is. We've got p of x equaling 1 over x and q of x equaling e to the x. Perfect. Do we have a y prime? Yes. First derivative plus 1 over x y equals e to the x. Yes, we're good. Okay, it's nice. We only have a first derivative. Nice. We have a y. That's great. Let's move on. What is I of x going to be? What's my integration factor going to be? here, I of x, e to the integral p of x dx. So let's look at that. That's going to be e to the integral of 1 over x dx, which the integral of 1 over x dx is natural log. So that's the natural log of x. There is a plus c, but we can ignore the plus c. Okay, and just think about it for positive x. And this is just going to equal x, okay, for positive x values, okay? So we're just going to treat it as x. I don't want to think about it as absolute value x. It's just we just need a function that works. We need a single function that works. We don't need all the cases and every single family of curves for this thing. Okay, I mean, this could be any linear curve. You know, if we really looked at it, we would get a c here, a cx. Okay, but we just need one. We just need one, need one function that works. Okay, it's my helper function. This is my helper function. And usually if we don't put the c in, we get a nice, not the nicest helper function that we can to create that product rule. We really want to create that product rule. Okay, so what are we going to do with this x here? Well, what are we going to do? We're going to multiply everything through by that x. We're going to take our dy dx, okay, plus 1 over xy equals e to the x, and we're going to multiply everything through by x. That's my helper function there, my helper polynomial, or my helper, I don't know what you call it, expression, I guess, you know, in terms of x. And so we're going to distribute, okay? And so this becomes x dy dx plus x over x, which is 1 times y, okay, equals x e to the x, okay? So now I want to think, well, what is this going to become? This is going to become xy, the derivative of xy. Why? Because again, if I take the derivative of the second function, that becomes my dy dx. Hold the first one in place, it becomes x. If I take the derivative of my first function, that's 1, which is this 1, that x over x becomes 1, times my second value, which is y. So again, this does create the product rule. Okay, so I take the derivative of this thing, that's the expression above. Okay, and so what do I want to do? To both sides, I want to integrate. Okay, so I'm going to integrate both sides. That means that I have xy is equal to the integral of this thing. And that's a very nice u substitution, or not u sub, integration by parts, like I said. U is equal to x, dv is equal to e to the x, v is equal to e to the x, and du is equal to dx. Okay, so we're going to integrate by parts there. uv x e to the x minus the integral of e to the x dx. Well, this becomes xy. Let's finish off this integration by parts. Minus e to the x, okay, plus c is equal to xy. Okay, and I'm going to divide, maybe divide through by, maybe I'll factor out the e to the x before I divide by x. Oh, I don't know. I guess we can just divide through by x because there's an x in the first term. It will be fine. Okay, so then we get y equals e to the x minus 1 over x e to the x plus c over x. And then I could factor out my e to the x, I guess. This is 1 minus 1 over x plus c over x. And there's a different ways to manipulate that. I could maybe find a common denominator. It really wouldn't simplify any further than that. per se. Okay, but that is my solution to that linear differential equation. Okay, solve dy dx equals 1 plus x, y is equal to e to the x. Now, could you check that? Absolutely, you could check that. You could find the derivative of this thing. Okay, you could take the derivative of this thing. I might want to take the derivative of the top of the function right above it. But if I take y prime, that should equal e to the x. Okay, minus, and there I would get a product rule here, right? So that would be minus the derivative of the second is e to the x times the first, that's 1 over x. Okay, plus the derivative 1 over x is going to be negative, I want to think, negative 1 over x squared. Negative 1 over x squared times e to the x. Okay, plus c, this is going to be minus c 1 over x squared. Okay, and so we will get the derivative there. And so what does that tell me? That tells me that dy dx plus 1 over xy should equal e to the x, right? So yeah, it should equal e to the x. Let's see if this works. Okay, so we know what the derivative is. It's that guy there. Okay, so the derivative is e to the x minus 1 over x e to the x plus minus plus 1 over x squared e to the x. Okay, minus c over x squared. Okay. Okay, and then plus 1 over x times y. Well, what was y? E to the x minus 1 over x e to the x plus c over x, right? Should equal e to the x. Okay, let's see if this works. So we're going to distribute the 1 over x. Okay, and we will get e to the x minus 1 over x e to the x plus 1 over x squared e to the x minus c over x squared plus distribute. We get 1 over x e to the x minus 1 over x squared e to the x plus c over x squared equals e to the x. And so, yeah, everything cancels. Negative 1 over x, positive 1 over x, positive 1 over x squared, negative 1 over x squared, and negative c over x squared, and positive c over x squared. And so what's left over? Just e to the x equals e to the x. And so it checks. Okay. That is, yeah, really good. Okay, let's do another one of these while we're at it. Okay, so we have number 2 here, dy dx plus xy equals x e to the x squared over 2. Okay, and we have an initial condition of y of 0 equals 1. Y not equals 1. Okay, so let's find out, well, what's our I going to be? Okay, so P of x is equal to x, Q of x is equal to x e to the x squared over 2. Okay. Okay. And so, yeah, this is going to be I of x is equal to e to the integral of p of x dx, which is equal to the integral of x dx. Okay, well, the integral x without the constant is, just let the constant be 0, is x squared. So this is e to the x squared over 2. Okay, so that's interesting. So what are we going to do? We're going to multiply everything through by e to the x squared over 2 dy dx plus x e to the x squared over 2y. Okay, good. Okay, and so, oops, I already distributed there. Let's just do xy. Okay, is equal to x times e to the x squared over 2 times e to the x squared over 2. Okay, so distribute. You've got e to the x squared over 2 dy dx plus x e to the x squared over 2y equals e to the x times, and we've got 2 of these now, so that's e to the x squared over 2, I want to say, times, means the whole thing squared, not just the exponent, okay, squared. So I'm going to end up multiplying the exponents here, and well, on the next line, these are going to cancel. Okay. So what is this going to become? Okay, remember that it becomes d dx of I of xy. That's why we do this. Okay, what's my I of x? Well, my I of x was e to the x squared over 2y. So this is e to the x squared over 2y d dx is equal to x e to the x squared. Okay, so now we want to integrate both sides. Okay, the integration and the differentiation, they undo each other. If I get e to the x squared over 2y is equal to, and then again, another integration by parts, u is equal to x, du is equal to dx, e to the x squared, if v is equal to e to the x squared, v is equal to e to the x squared, the derivative of, oh, I don't even need to do integration by parts here, do I? No, if I just do a regular u sub, I think it will work. Yeah, no integration by parts necessary. That's nice. So u is equal to x squared, du is equal to 2x dx divided by 2. Yeah, that's great. Okay. So, oops. So e to the x squared over 2y is equal to the integral of e to the u du over 2. Okay, well, the integral of e to the u is just e to the u. So this is going to be 1/2 e to the u plus c. Okay, but what was u? U was x squared, right? Okay, so we've got e to the x squared over 2, y equals 1/2 e to the x squared plus c. Okay. That's good. Good. I like what I've done there. Okay, so let's divide by e to the x squared over 2, divide by e to the x squared over 2, divide by e to the x squared over 2. Okay, so this is going to become, okay, we've got, think of it like this. We've got 1x squared on top, and we've got 1/2 x squared on the bottom. That should leave me with a 1/2 x squared when I divide. Okay, so this is 1/2 e to the x squared over 2 plus c e to the negative x squared over 2. That guy's on the bottom. Okay, is equal to y. Okay. Okay, so that would be my general solution, but they give me a an initial condition here. Okay, which is interesting. Okay, so what's the initial condition? The initial condition is y at when x is 0, y is 1. Okay, so when x is 0, y is 1. Okay, so we have y naught is equal to 1. Okay, so 1 is equal to 1/2 e to the 0 squared over 2 plus c e to the negative 0 squared over 2. Okay, interesting. Okay, and so we get 1 equals 1/2 e to the 0 squared plus c e to the negative 0 squared. The e to the 0 squareds and the e to the negative 0, those are going to go to 1. Okay, and so I get 1 equals 1/2 plus c, subtract 1/2, and we just get 1/2 equals c. Okay, what is that going to do? We just get y equals 1/2 e to the x squared over 2 plus 1/2 e to the negative x squared over 2. That's interesting. Maybe if I write that as over a common denominator, you'll see that this is actually a pretty familiar function. So if y equals e to the x squared over 2 plus e to the negative x squared over 2 all over 2. And this is actually the hyperbolic cosine function. Remember, if we have, say, y equals e to the x plus e to the negative x over 2, that is the hyperbolic cosine of x. So instead of the x's, we actually have x squared over 2. And so y is equal to the hyperbolic cosine of x squared over 2. Okay, for that one. Okay, example number 3. Okay, it says that we want to solve x dy dx minus 2y equals 2x squared ln x. And this is for when x is greater than 0, otherwise we have messy natural logs, and we have initial condition y of 1 is equal to 1. Okay, so we'll get a general solution and a particular solution for this one as well. Okay, let's divide through by x. Okay, so dy dx minus 2 over xy is equal to 2x natural log x. Okay, so I want to I'm going to change this to a positive and then the negative. I want to make sure that my p of x is representative of just the negative 2 over x. Okay, so what's I of x going to be? I of x is equal to e to the p of x dx, right? Okay, so this is going to be equal to e to the integral of negative 2 over x. I could pull the -2 out if I wanted to. Okay, dx. E to the -2 integral 1 over x dx. That's going to give me natural log of x, right? That's going to give me natural log of x. So dx. So this is going to be equal to e to the -2 natural log of x. And then what I'm going to do is use the property of natural logs to put that -2 as the exponent of x. So this is actually e to the natural log of x to the -2nd power. And now I can cancel the natural log and the e, and that just gives me e to the, or sorry, x to the -2nd power. You can write it like that. I'll probably leave it like that, or you could write it like that. Okay, I think I'm going to use e to the -2. I think it's just going to make things a little nicer. Okay, so let's take my integration factor and multiply through my original differential equation. 2x times natural log of x times x to the -2 power. Okay, so this is going to become x to the -2 dy dx. If I distribute, that becomes x to the -2 x to the -3, which is nice because that is actually the derivative of x to the -2. Perfect. Y equals, this is going to become 2x to the -1st power natural log of x. Okay, so we've got d dx of x to the -2 y, okay, is equal to 2 x to the -1st power natural log of x. Okay. Okay, and then what we can do here is we can then integrate both sides with respect to x. And we get x to the -2y equals, now, this is, I want to pull the 2 out in front. Okay, and this becomes 1 over x natural log of x. Okay, and at first you might think, again, we should use integration by parts here. However, a simple u sub might be helpful. If we let u equal natural log of x, then du is actually just 1 over x dx. Okay, so we're actually just taking 2 times the integral of u du. Oh, that's nice. That's nice and helpful. Okay, so x to the -2y equals 2 u. Well, that's just u squared over 2, right? So this equals 2 times u squared over 2, plus c. Okay, plus c. The 2's are going to cancel. I could distribute the 2 if I really wanted to, but 2c and c are the same. It's just a constant. Okay, so this becomes u squared plus c. But what is u? U was natural log of x. So that's natural log of x squared plus c, some constant c. Okay, and we get x then to the -2 power y equals that. And so if I were to divide by x to the -2, that would be the same as multiplying by x squared. So if I just multiply both sides by x squared, everything here by x squared, those will cancel out, and I'll be left with y equals x squared natural log of x squared, okay, plus x squared times c, or cx squared. And I could actually bring everything under 1 squared if I really wanted to. you know, I've said, oh, this is x ln x squared, you know, plus cx squared. Okay, so this is my general solution. Okay, so let's go for that particular solution. Okay, what is my particular solution going to be? Okay, so y of 1, okay, y of 1 is equal to 1, right? Yeah, y of 1 is equal to 1. Okay, so we're going to plug in and let x equal 1 here. Okay, so 1, y is 1, when x is 1, that's 1 natural log of 1 squared plus c times 1 squared. Okay, so 1 is equal to, well, this thing's just going to go to 0 because the natural log of 1 is 0 plus c times, well, just c. So c is 1. So we get y equals x natural log of x squared plus x squared. And I could leave it like that, or I could maybe pull out the x squared. Okay, so y equals x squared ln x squared plus x squared. So then we get y equals x squared times natural log of x quantity squared plus 1. Okay, and both problems 2 and 3, you could plug these values. You could take the derivative of these functions and then plug that back into my differential equation. You could check them. I'm not going to take the time to check them, but they do work if you were to check your answers. Okay. Okay, so that's 1.6, and I will see you in the next video.